Flack math! Give me some math and I'll give you some flack. Flack math!
So, 71 and 72 today. Don't forget your tests are due tonight, so make sure that's done. Your test is done tonight before midnight. If we have time today, we might have time for questions if you have some last minute questions on your test. So yeah, so we're gonna do 71 and 72, and we just have homework of 71, 72, and 74 for homework. Okay, so we started talking about one of my favorite topics. We're talking about trinomials, factoring trinomials. Let's put one on the board just for practice because it's fun. So do you guys know how to factor this trinomial? What do you start with? What awkward thing do you start with? Cheeks and tats. Yeah. All right, so let's throw those up there. And Eliana, we won't CGI anything out of that. So, okay. All right, now what's the magic question? What do you ask yourself? Yes. Okay, so there's some different options. 1 times 18, 18 to, oh, we don't have to do 18 times 1, but we could do -1 times -18, right? But I don't think any of the negatives are going to add to a positive, right? So we're going to get rid of that. 2 times 9, 3 times 6. We have 3 options. So which one is it? 3 and 6. Let's try it. So when we put 3 and 6 here, and then we FOIL it out, we get x squared plus 6x plus 3x plus 9. These add together because they're like terms. Not 9. 18. Oh, what the? 9x plus 18. So that works, right? Okay. If you don't remember the magic question or whatever, what you do just need to remember is this question. What are the factors of 18? Okay, so that's these two numbers. Whenever you're multiplying a binomial times a binomial, these two numbers always multiply to get that last term. So just try each one of those and then FOIL it out and see which one works. Okay, that's not a shortcut, but it helps you learn it. And your brain will do that about 4 or 5 times and then tell you that they're done. Your brain's done. There's an easier way to do this. I'm going to figure it out. Okay, so your brain is going to do the work for you, obviously, but your brain is going to develop that own shortcut. Okay, so let's move on to the next thing. So the first step, though, to factoring, so do you know how, like, when you have something like this, 36, you can factor 36. What times what is 36?
6.
6 times 6, right? And then those can be factored more, right? So then sometimes you have to factor in a couple steps, all right? Or like, I don't know, 12 is 3 times 4, but then 4 is 2 times 2. So 12 is 3 times 2 times 2. So sometimes there's more than one step to factoring. This is just one step. So if I did this like a factor tree, it would look like this, right? because that times that equals that. But that's it. You can't factor x plus 3 anymore. Nothing times nothing equals x plus 3. It's just a factor. It doesn't look like those, but it's a factor. It's a chubby factor, but it's a factor. Okay? Here's another chubby factor. Those two factors equal this when you multiply them together. Okay? So what does it look like when you're factoring in multiple steps in algebra? All right, well, let's try that. Let's say that instead of x squared something, I've got x cubed something. Okay? Well, we don't know how to factor a cubic polynomial. Okay? But the first step of factoring is something that we learned a month ago, is taking out a greatest common factor. What goes into all three of those? X. So see how x didn't go into all three of those. But x does go into all three of these. When you take an x out, you're left with x squared plus 6x plus 5. Right? So this is kind of like this happening. All right, now we can do this. This is a factorable trinomial. You know what it is? 2 and 3. So this is yep, you caught yourself. But that's what most people see when they look at that. So you're in the norm there. But what is it? It's not 2 and 3. It's on your lips. You were about to say it. You put your lips together with your teeth over your bottom lip. What number is that? Put your teeth over your bottom lip. 5. 5 and 1, right? Because 5 times 1 is 5, but 5 plus 1 is 6. Okay?
What about the x?
Well, when you FOIL it out, what about this x? Or when you FOIL this out, yeah. When you FOIL it out, you get x squared, and then 1x and 5x add to get 6x. So there's the x. And then 5 times 1 is 5. Okay? So do about 10 of those and you'll get it. Okay? And then it's just fun because they're like riddles. All right? So, but this one is still a factor. So this is our complete factorization. Just like when we had 12, it wasn't 3 times 4. Or it wasn't even 2 times 2, it was 3 times 2 times 2, right? So now you have to put all the factors together. You remember how we did that when we did factor trees, and then we had like 2 to the third times 3 to the fifth, you know, all those back in pre-algebra when you list it out at the end. That's what we're doing here. There's just 3 factors, x plus 5, and x plus 1. That's it. So once you get that x out, you can kind of forget about it, but don't forget about it completely because that needs to go in your final answer, okay? All right, let's try another one. Let's try this one. 4bx cubed minus 4bx squared minus 80bx. Okay, that looks confusing because we need to do the first step of factoring. Always look for a GCF. So what goes into all 3 of those? B and X both go into all 3 of those. What else? Yep, always look. So you're looking for 2 things, numerically and literally. Okay, you're looking for the numerical factors that go into everything. So the number 4 goes into all 3 of those. Sometimes you get it, sometimes you don't. We didn't have a numerical GCF over here, but we do have a numerical and we have a literal. We have 2 literals. We have B goes into all of them and 1x you can take out of all of them, right? So when you do that, what are you left with? Let's see. You take the B out and you don't have a B anymore. Take 1x, you take the 4 out and you don't have a 4 anymore. You take 1x out and you're left with x squared. So this, you're just left with an x, right? Take a 4 out of 80, that's 20, right? You're not subtracting the numerical factors, you're dividing them. So that's 20 And then b and x, you take them out and you're gone. All right, can we finish it? So what factors of negative 20 add to get negative 1? How can you add to get negative 1? Right, because there's no number here, so that's a negative 1, right? How can you add to get negative 1? What two numbers add to get negative 1?
Negative 2 and 1.
Negative 2 and 1, right. But negative 2 times 1 equals,
Well,
doesn't equal.
Isn't there
right. So now what factors of negative 20 will add to get negative 1? Can't think of it. We can just start listing factors of 20. What are factors of 20? 1 times 20?
Or negative 20.
Negative 20.
Okay.
Yeah, so like negative 1 times 20 or 1 times negative 20. There's an option, right?
Yeah.
What else? Negative 2 times 10.
2 times negative.
Okay, what else?
5 times 4, or 5 times negative 4, and then negative 5 times 4.
Because look at negative 5 added to positive 4 is what? Negative 1. Okay? So x minus 5 and then x plus 4. Those are your factors. Okay? Now, if you're still not following this, FOIL this out. Multiply it out and your brain will connect the dots. Well, I don't have to touch that, but over here I'm going to go x squared plus 4x minus 5x. Okay, well, plus 4x minus 5x, those combine to negative 1x. Oh, there's that. And then the last term, negative 5 times 4 is negative 20. That works. Okay, so final answer looks like this. That's the final factorization of that crazy mess up there. Okay. So now, when I look at that, I can tell you, I don't know how to factor this. I don't know how. But I do know the greatest common factor. I can figure that out. Okay? But I can't do this, but I can do this. And when I'm done with that, I can do this. And that doesn't even apply to this one, so now I can do this. And then that nice little magic question, what factors of the constant of the last term add to get the middle term's coefficient? Okay, so I can do that one step at a time. These are your steps to factor, okay? Always look for a GCF. Look for a difference of 2 squares, which we'll get to later. But right now, we're just doing steps 1 and 3. That's just 2 steps. I can do that. I can handle that. But I can't do it. I can't give you the answer right now. If I look at that, I can't give you the answer. But I can give you the answer to the first step. I can find the GCF. So can you. Okay? So don't stress about doing this problem. Just worry about doing the first step. Okay? Does that make sense? All right. Moving on. Now, the other annoying thing that you might find is when the first term, like the x squared term, is a negative number or negative, then that's annoying. So we're going to fix that. So is there anything that goes into all 3 of these? Say it. Yeah, you always say it. You always do it with your lips and then you stop. So yeah, 1 goes into all 3 of those, but that doesn't really help us, right? Because you take a 1 out, you're left with the same thing. But if I take a negative 1 out, then I'm going to be left with a positive x squared. So that's what I want to do first, which is kind of annoying that it looks like this, but we can't factor this yet because it's got a negative x squared term. So factor out a negative 1 first. Does that make sense? Because if you multiply -1 times everything, you'll get this. But the only reason we did that is now we have a positive x squared term. Okay, and we already factored this, right? That looks like this, doesn't it? So this final factorization will look like this. Okay, and then you're done. All right, so if that x squared term is a negative, take it out. Now sometimes it's kind of nice since you have to take stuff out anyway. Like if this was a -4bx cubed, well, instead of taking out a 4bx, you take out a -4bx, right? So you kind of killed two birds with one stone. You made the first term positive and you took out the greatest common factor, okay? All right. So there's more. You'll get lots of practice when you do this in your homework, but yeah. So if you're just kind of getting it, that's an okay place to be. All right. The last part of lesson 71 talks about subscripted variables, which is helpful, but I think Saxon kind of overemphasizes it, so it's not. Remember when we used to say what % of 80 is 60, and then we had to translate, right? We had to say what % of 80 is 60. Remember doing those problems? Okay, well, Saxon says, well, what % of 80 is 60? So they use subscripted variables. So this is not W times P. This is W subscript P, which kind of makes sense. What %? I mean, but do you see how that's kind of overdone with Saxon? Just choose P, right? This is kind of just an extra emphasis on the reminder that when you get your answer, you have to convert it to a %. You're going to get a decimal here, right? 0.75. But since it's WP equals 0.75, oh, I'm looking for a %. So that's a reminder to move the decimal over 2 places. It's not 0.75, it's 75%, okay? Now, these subscriptive variables will come in handy later for sure when we start talking about uniform motion, because we talk about distance, rate, and time of unit. You remember distance equals rate times time. That's uniform motion problems. Like one train left the station at 4 p.m. and going 50 miles per hour. The other train left, those kind of problems, all right? I always hated those problems when I was a kid, but algebra makes it easier to do those problems, okay? And since we've got 2 different trains, we need 2 different rates, we need 2 different times, and we need 2 different distances sometimes. So we say D1, R1, T1, okay? And we say D2, wait for it, R2, T2. Isn't that awesome? R2, D2. Okay. Anyway, so what Saxon does next is that we do coin problems. And this, you don't have to figure out the equations yet. You just have to start practicing working with subscripted variables, okay? So let's say that there are 16 dimes and nickels. 16 dimes and nickels. Now, you don't know how many are dimes and how many are nickels, right? So there could be 1 dime and 15 nickels. There could be 2 dimes and 14 nickels, right? There could be 15 dimes and 1 nickel. There can't be 16 dimes and 0 nickels. There can't be 0 dimes and 16 nickels. So really you just have 15 choices, right? 15 and 1, 14 and 2, 13 and 3, right? All the way up to 15, right? Or down to 1 and 15. So you only have 15 combinations. So you could try to figure out what they're talking about, but you need more information. You don't know the rest of the riddle. Here's the rest of the riddle. 16 dimes and nickels are worth $1.25. So you could go through all of your options So 15 dimes is $1.50 and 1 nickel is $1.20. That's too high. So let's do less dimes. Let's do, let's say 10 dimes. Well, that's $1. And then 6 nickels would be 30 cents, right? So $1.30 is still too high. So I think 9 dimes and 7 nickels. What's 9 dimes? 90 cents. 7 nickels is 35 cents. That works, okay? So you could go through all of your 15 options, and like I said, your brain is gonna make a shortcut. It's gonna say, oh, that's too many dimes. If it goes over $1.25, there's too many dimes. You gotta have less dimes and more nickels if you want the price to go lower, right? I'd rather have more dimes than nickels, but this is what the problem says, right? So now here's what Saxon says. They say, okay, the number of dimes and nickels, the number of dimes plus the number of nickels is 16. That does not tell you the value of how much money you have, right? So if you gave your little sibling who doesn't know money 16 dimes and nickels, they'd probably look at the nickels and say, oh, I like these better because they're bigger and they're heavier. And they're probably worth more, right? Okay. So when you do number of dimes and nickels, you have to forget about cost, like the value of it. But 16 dimes and nickels, here's an equation that says this. 16 dimes and nickels, if I translate that into an algebraic equation, I could say number of dimes plus number of nickels equals 16. Now, what I usually do is I just say capital D plus capital N equals 16. But this subscripted variable emphasizes that it's not the value of the dimes and nickels. It's the number of dimes and number of nickels. So that's why these subscript variables might be a better way to go when you're talking about money, because you're not talking about the value, you're talking about the number, okay? Now, how do you calculate the value? Well, how do you if you had a number of dimes, how do you calculate the value of those dimes? Let's say you don't know how many dimes you have, but how do you calculate the value of those dimes? What do you do? Well, let's pick a number. Let's say you have 438 dimes. How much money is that?
4,000.
Yeah, what did you do? What kind of math did you do?
Multiplied by 10.
Multiplied by 10. So now if I want to go, this is my quantity equation, number of dimes, number of nickels. Now if I wanted to do a value equation to figure out the value of that number of dimes, I multiply by 10. Oops. So 10 times the number of dimes gives you the value. So now we're writing a value equation. And that value, remember, has to equal 125 cents. So since dimes, we could keep it in terms of dollars, right? So we'd have to say 0.1. Don't do that. Let's just convert that to cents, 125 cents. Okay, how do you calculate your nickels? The value of your nickels, what do you do? 5 times the number of nickels, so plus 5 times the number of nickels has to equal 125 cents, okay? So now what do we have here? You've got a system of equations. You've got 2 different equations with 2 variables. So if I want to solve by substitution, I look for the most vulnerable variable. Looks like one of these I can easily get by itself, right? So let's just get one of these by itself. Let's get the dimes by itself. The number of dimes, oops. Number of dimes equals 16 minus number of nickels, right? So I just got rid of that, put it over there, subtract it from both sides. Number of dimes equals 16 minus the number of nickels. So far, so good? So that's what I'm going to substitute in right there. So now I'm going to rewrite this equation. 10 times number of dimes which is equal to 16 minus number of nickels, plus 5 times the number of nickels equals 125. Okay? Simplify and solve. So you get 160 minus 10 number of nickels plus 5 times the number of nickels equals 125. So that's 160 minus 5 times the number of nickels. So I'm going to come over here and finish it. So 160 minus 5 times the number of nickels equals 125. Okay, get rid of that 160. Okay, 160 is bigger than 125, so you're going to end up with a negative number. 5 times the number of nickels equals negative 35. Divide both sides by negative 5, right? I'm just doing what we've been doing the last few weeks. It just looks a little different because of this subscripted variable. So number of nickels is 7. Now I've got my number of nickels. I can plug it in right there. Number of dimes is 16 minus 7, which is 9. Okay? Number of dimes equals 16 minus 7, which is 9. Okay, so this is just using subscripted variable. Don't worry too much about forming these equations yet. You might have to do a little bit of that, but they just want you to kind of get into the habit of using subscripted variables. Okay? Did I do that problem wrong? What's the deal? Oh, yeah. Example 6 is another one. We can do another. Let's do another one. Let's see if you guys can do this by yourself. Okay, I'm going to leave this one on the board so you have an example to follow. Oops, I lied. There it is. All right, so here is example 6. And it just starts with this. You don't have to come up with the equation. It just starts with this. 5NQ. What do you think Q stands for?
Quarters.
Yeah, except that's nickel. And then 25, because you wouldn't multiply a number of quarters times 5. You multiply your number of quarters times 25, right? Equals 290. And then your number of nickels plus number of quarters is, oh, no, this is what this would say. So this is, when you do have to figure this out, it would say, let's say your number of quarters, you have 2 more quarters than nickels. Right? So you could get something like this, which is nice because it already gives you your number of quarters. It already has one of the variables by itself. So now just plug it into there and go for it. So try this one. What do you get? didn't give you the word problem. But if they did, it probably sounds something like this. The value of the dime or nickels and quarters is $2.90. Okay? But there are 2 more quarters than nickels. So that gives you enough information to figure it out. Now you could just go through all the options. I mean, 2 more quarters than nickels, you could have 3 quarters and 1 nickel. Well, that's 75 cents plus 5 cents, which is 80 cents. That's too low. So you need more. Maybe 10 quarters and 8 nickels, right? Well, 10 quarters is $2.50 and 8 nickels, 40 cents. So that's the right answer. So what'd you guys get? Did you get that? All right, so I'm just going to plug this sucker in right there because that's what NQ is. N subscript Q is N subscript N plus 2. So I'm going to replace that. So I'm going to rewrite this equation. 5 times number of nickels plus 25 times number of quarters equals 290. All right, simplify and solve. 5 NN plus 25 NN plus 50 equals 290. Okay, combine like terms, get rid of that 50. So 30 NN equals 240. NN equals 8. If NN equals 8, NQ equals 10.
Yeah.
Does that make sense?
It's basically the same thing as the other thing.
Yeah, basically the same thing that we've been doing for the last few weeks. Instead of X's and Y's, we have NNs and NQs and NDs and all that stuff. Okay? Yes.
Should I like make it a habit to write NN, or can I just write N?
That's what I do. I just write N.
That's what I did.
Because it's not like you have a different subscript of variables that's talking about the value of NN. So I just do N and Q. Okay? But this is just a good annoying reminder. Like it's gonna be annoying to write it because when you write NN, you're not writing the value of your nickels, right? You're just expressing the number of nickels. So it's one of those subscript things that are annoying to do, but if you can do it without subscripts, then that's what I normally do because it's annoying to just write NN, NQ, NQ, NN, ND. It's annoying. Okay, you guys good on 71? All right, let's move on to 72. All right, 72 is just factors that are sums. Now, here's what I mean by that. Let's just write one on the board. So these are just these factors. Remember, these are still factors. They're just chubby factors. Okay? Because this is being multiplied by something. That's the definition of a factor. Something that's being multiplied. So, do all 3 of these terms have something in common? Can you take something out of all 3 of these terms?
A plus B, right?
Yeah, that's still a factor. Don't judge this factor just because it's a chubby factor. You can take it out, all right? They all 3 have A plus B in it. So let's take it out. Do what we normally do and take out that A plus B. So here's my GCF. Okay, And then what am I left with? Right? So this is what we're doing right here. First step. Okay? Now the GCF just happens to be a chubby factor, but that's okay. You take an a plus b out of there, what are you left with? X squared. Take an a plus b out of there, what are you left with? A negative x. Take an a plus b out of there, you're left with a negative 6. So far, so good? Are you done? No, because look, you can factor that. That's a trinomial. There are factors of negative 6 that add to get negative 1. What are they?
Negative 1 and 6, right?
So negative 1 times 6 is negative 6, but negative 1 plus 6 is positive 5. You're getting it. So your brain's working out the details of figuring this out. What'd you get? Yep, so x minus 3, x plus 2, because negative 3 times 2 is negative 6, but 2x and negative 3x combine to a negative 1x. Okay? Now, this is not a concept that you're going to understand if you just look at me. Okay? You have to do this homework. You have to factor about 10 to 15 trinomials, and then it will click. Okay? So, if you don't understand this yet, do the work. Do the time. It works every time. I can't rhyme. Hey, I just did. Okay. All right. Let's try another one. Example 2. So let's factor this guy completely, okay? Ready, go. All right, I'm moving in. What can you take out?
X plus y.
An x plus y. I'm going to take this sucker out here. So I get an x plus y. Take that out. What are you left with? Yeah, x squared plus 9x. This is nice because all you have to do is just get rid of it. All right. Now, can you figure this out?
I did 4 and 5.
Yep, that's it. So 4 times 5 equals 20, but 4 plus 5 is 9. So then our final factorization looks like this. X plus 5, x plus 4. So your brain, if you don't get this yet, multiply that out. And you'll see, and your brain will put it together. Okay. I think we've exhausted this enough. So sometimes, like if for some reason we had like another m, like just another variable here. That's okay. We can take an m out of all of that too, right? And then you're left with an m here. So it doesn't have to be just chubby factors or just little factors. You can take out whatever they have in all three of those terms, you can take out. Okay? Good? All right. That's, sorry. The last part is easy, but it's just the last part of 72, which is finding the volume of pyramids and cones. Pyramids and cones are just like prisms and cylinders, except they are a third of the volume every time. Every time they're just exactly a third of the volume. Okay? So if I had a rectangular prism that looks like this, then if I had the same thing, but it was a pyramid, so that ended right here, right? So this is the same, if this is the same height, so if they have the same height, then you could fit 3 of these inside of here. Not physically because it's awkward shape, right? But if I were to ground that to dust, I could fit 3 of those inside of this prism, okay? So every time, that's what makes this easy. So if this is volume equals area of base times height, right? Area of base times height. This is volume equals 1/3 area of base times height. Every time, okay? So that's easy because that base is like a rectangle, length times width. The height is, they're going to give you a height, and then just divide it by 3 and you're done. Okay? So that's finding the volume. Surface area, well, surface area is not terrible either, right? You just have to know the height of each of these individual triangles and things like that. But also, it works the same way with cones. Right? You can fit 3 cones inside of a cylinder. So if this is area of base, which is pi r squared, times height, then this would be 1/3 pi r squared h. Okay? Pretty simple. Volume is nice because it's usually a really simple equation. Surface area is where it gets weird. Okay? Now, that's what I'm going to spend most of this time talking about. Surface area is still like this guy, finding the surface area of a prism. You could find the area of all 6 faces, right? And then add them together. But remember that shortcut was you could find the area of the top, which is the same as the bottom. And then this rectangle that wraps around the whole thing has a dimension of the perimeter of the rectangle and then the height, right? So really it's just 2 math problems. Find the area of the top and then double it. And then find the area of the lateral area, which is just perimeter times height, and you're done. Works the same way with cylinders, except remember their snobby language is not perimeter times height, but circumference times height. So area of the top, double it, so pi r squared times 2. And then the area of that rectangle, so circumference times height, so pi d h, right? Now, here's the cool thing. Well, it's not necessarily cool. To find the surface area, it's a little bit trickier. Now, over here, you can just find the area sum of all faces, right? So that's kind of, there's another way to do it that we'll learn in geometry. But for now, just find the area of all the faces. Now, it has to give you this length, which is called the slant height. It's not the height of the pyramid, right? The height of the pyramid is this guy right here, or the altitude is what they call it sometimes. Okay, but the slant height is the height of one of those triangles, but it's leaning, right? So we call it the slant height. So that's not how high it is because it's leaning. So that's just the two-dimensional height of the triangle. But you need to know that, right? If you want to find the area of all the sides, that side is a triangle. That face is a triangle. So to find the area of that, you need to know that slant height, okay? Now, these guys have a slant height as well. Okay, now to find the surface area, if you were to unwrap this, it would look like this. You got the base plus this weird thing here. If you were to unwrap that cone, it would look like that. Okay? So, how do you find the area of that? Area equals base times height divided by 2, right? Or 1/2 base times height. That's how you find the area of a triangle, even though it's a weird curvy looking triangle. 1/2 base times height. Well, this is the slant height. And what's this length here? That's like the perimeter, or in snobby circle language, we call it the circumference. Okay, so how do you find the circumference? That's 1/2, or the circumference would be pi times d times, and then times L, which is the height, okay? So 1/2 pi dl. Well, look what we can do. What's 1/2 of d? What's d stand for? In a circle, what's d stand for?
Diameter.
So what's 1/2 of a diameter? Radius. So this is just r. So we could say area of this thing is pi r l. Because the height is the slant height, L. And so 1/2 d is pi, so is r, so pi r l. Okay, so the surface area of any cone is this. So cone surface area equals the base, which is always pi r squared, right? That's how you find the area of all bases of a cone, because all bases are a circle, plus the lateral area, which is pi r l. Okay? Now, let's just do one example, and then I think you got it. I don't think we're not gonna do an example on how to find the surface area of this, because you just find the surface area of all, in this case, it'd be 5 faces, right? The bottom, then the 4 lateral faces. Well, let's find the surface area of this cone. So let's say we've got a cone that looks like this. So let's say this is 10 meters. And then let's say that we've got a radius of 8 meters. Now here's the cool thing. We don't even need to know the height of that cone to find the surface area. We could find the height. I mean, let's just put the height in there. Let's say that it's 6 meters. Okay? I drew that a little weird, so the 6 is a little bit longer than the 8, but how do you find the volume of a cone? How do you find the volume?
Volume is pi r squared divided by 3.
Yep.
Or is pi r squared times height divided by
Yep,
3.
that's right. Okay, so I'm just going to write it like this: 1/3 pi r squared h, which is what you just said. So I'm going to do that. Let's see here. 1/3 pi 64 6. Right? That's 1/3 pi r squared h. Well, 1/3 of 6 is 2. So volume equals 128 pi. or I can multiply it out if I wanted to, multiply by 3.14 to get an estimation. You can do that. Okay, now let's find the surface area. How do you find the surface area? Right there. Okay, so surface area equals pi r squared, so pi times 64 plus pi rl, so pi times 8 times 10. Okay? So far, so good. I just plugged it into this formula. So then you get 64 pi plus 80 pi, which is 144 pi. You can multiply it out if you want to get an estimation, but that's it. Okay? This would be square meters, but this one would be cubic meters, right? Because it's volume. All right, any questions with this? Write this guy down especially. You can write this. This is the same for pyramids and cones, but we can simplify it even more in a cone because the area of the base is always pi r squared. But this, it just depends on the base. The pyramid just depends on the base. Okay, you guys good? All right.
Black math, give me some math and I'll give you some flack. Black math.